Assalamu alaikum wa rahmatullahi wa barakatuh. So we continue the topic of designing dosage regimen. We stopped yesterday by this slide. So now we will learn how to calculate the average plasma drug concentration at steady state in case of administration by IV bolus injection. When we say here average concentration, don't get confused. Average here doesn't mean arithmetic average. So, for example, for IV bolus regimen, we have Cmax and we have Cmin, so you may think that we just add Cmax plus Cmin divided by 2. So there they give the average, right? No, that is not correct. When we talk about average concentration, this is a concentration that will give idea about the average exposure during the dosage interval. And it is mainly expressed as AUC divided by tau. So the length of the dosage interval is tau, right? And the exposure during AUC is during the dosage interval is represented by the area under the curve between the two doses. Okay, so we divide this area under the curve by tau, then the result is the average concentration. And the equation can have other forms because AUC can be replaced by this value, for example, FD divided by clearance. This is equal to AUC. Can be also replaced by, the clearance will be replaced by K times VD. Okay, so we have different forms we can use for calculation of average concentration in case of IV bolus at steady state. As an example, let's practice. The problem here, or this example, a patient received a dose of 1000 milligram of antibiotic every 6 hours by IV bolus injection. Knowing that the volume of distribution is 20 liters and T half is 3 hours, estimate the average steady state drug concentration. So we can calculate using one of these forms, depends on the data we have here. So the data we have here is T half and volume of distribution. You cannot find T half in any of these, but you can find K, which is related to T half. So first we calculate K. K is equal to 0.693 divided by T half equal to 0.693 divided by 3 hours. So this is the value of K. Then we can use this form. CP average plasma drug concentration, the average plasma drug concentration at steady state equal to F dose divided by K VD and times tau. VD we have from that problem. K we calculated already. Dose is given. How about F? We mentioned before that F is the bioavailability fraction, and bioavailable fraction for in case of IV administration should be equal to 1 because the whole dose has been delivered to the systemic circulation, right? So F is 1 because we can use this equation later on in the oral dosing. So in case of oral dosing, then the bioavailability may be less than 1, but in IV it is equal to 1. So just substitute the values. 1 times 1000 milligram divided by K times volume distribution 20 liters times the tau 6 hours. So the average plasma concentration is 36.08 milligram per liter. For the same dose and dosage interval, if you calculate Cmax, it will be higher than the average concentration, and if you calculate Cmin, it will be lower than the average concentration. Okay, here also another probability of plasma drug concentration is if the patient, for example, missed one dose after taking multiple doses. So can you calculate the plasma drug level? If you remember that we mentioned that with the administration of doses, with multiple doses, then the concentration is going to keep increasing till it will reach a steady state concentration where the range will be fixed, Cmax and Cmin will be stable. Okay? So what happens if, for example, one dose here was missed? The increase will not continue because there will be longer duration where the drug will be eliminated. So it will be like this. And then the next dose will cause some increase. Okay? So it will give lower concentrations than if the dosing is continuous. So how to calculate? There are two equations. One can be used in case of missed dose before steady state achieved, and the other one can be used if the missed dose is at steady state. Here the decrease will be from the concentration in this area, and for steady state the decrease will be from the expected steady state levels. Okay, so as I mentioned, you don't need to memorize these equations, but you have to understand what are the values included inside. So up till here it is the same form, like almost like before, that when we calculated the concentration from certain dose before steady state and at steady state. But here we add, so here the number of doses, n is the number of doses. In steady state concentration, in steady state equation, we don't have the term number of doses. This is the elimination fraction. So this is the like Cmax portion, and this one give you the random level. But here we minus this fraction that represent the drop in concentration due to the dose missed. So Tmiss is calculated from the time elapsed since the scheduled dose was missed. Okay, so this is, we add another elimination fraction, means we add another elimination fraction. Let's practice solve a problem so that we make this clear. So for example, here a cephalosporin with pharmacokinetic parameters k equal to 0.2 hour to the power minus 1, Vd equal to 10 liters, was administered by IV multiple dosing. 100 milligram was injected every 6 hours for 6 doses. What was the plasma drug concentration 4 hours after the 6th dose? If the 5th dose was omitted, the 6th dose was omitted, or the 4th dose was omitted. So we have 3 probabilities we want to calculate. But in all of them, it is mentioned that dose number 6 was omitted. Okay? What was the plasma drug concentration 4 hours after the 6th dose? If also. So for all of them, they want the concentration after the 6th dose, 4 hours after the 6th dose. Okay? But the omitted dose is different. So first we want to know whether we achieved steady state or no, so that which equation we are going to use. So to know steady state achieved or no, first you need to calculate the T-half, right? We don't have the T-half, so it is better that you first calculate the T-half. So T-half equal to 0.693 divided by K, which is 0.2. So how much is the half-life? How much is the half-life? Equal to 3.46 or 47 hours. Okay, so we said how many half-lives we need in order to achieve the steady state. We say at least 5 half-lives, so you need steady state time to steady state equal to 5 times 3.47. So at least you need 17 hours to pass from the first dose in order to achieve the steady state. So here he's asking about the sixth dose. Okay, so when we say sixth dose, how many dosage interval passed? Usually not 6 dosage intervals, only 5, because here you have time 0, 1 dose. At 1 dosage interval, 1 tau, 2 doses. 2 taus, 2 dosage intervals, 3 doses, and so on. So if you have 6 doses, means 5 taus have passed, right? And the dosage interval here is 6 hours. So 5 times 6 equal to 30 hours. So now time to reach steady state is 17 hours. And then if you ask about after 6 dose, then you are talking about 30 hours. Means steady state has been achieved, right? So in this case, actually you can straightforward use the equation for steady state, which is simple. As I explained before, if you use non-steady state equation, still it will give accurate calculations, but the equation is bulky. Okay, so it's up to you to use either of the two equations, and you can compare the results using both. You can find that you get a similar results. So at steady state you can use non-steady state or steady state equation, they will give similar results. But if steady state not achieved, definitely you cannot use steady state equation, you will have error. Okay, so steady state, non-steady state equation can be used all the time, but steady state equation can be only used at steady state. So now if we apply in this equation, so dose is 100 milligram, volume distribution is 10 liter as given, and the number of doses is always 6 in all the in all the problems. The k is the same, tau is the same. Here also k and tau the same. So what will be the difference? The difference will be in this fraction, the TMS. The difference will be in the TMS. Okay. So previously we mentioned that in our definition, TMS is the time elapsed since the scheduled dose was missed. Since the scheduled dose was missed. So we go back to this line here, and let's see how to calculate this time elapsed since the dose was missed. 4 doses and then 5 doses. The time here is 0. 1 tau means 6 hours. 2 taus is 12, 18, 24, and 30 hours. And then they want to calculate after the 6th dose, means at 34 hours. Okay? So when the 5th dose was missed, where is dose number 5? This is dose number 5. What is the time between the time we want to determine our concentration and the time the dose was missed? From 24 to 34 is 10 hours. So here the time is 10 hours. The 6th dose was omitted. So between the 6th dose, 30 hours and 34 hours, we have how many hours? We have 4 hours. So the time TMS is 4 hours. C, the 4th dose was omitted. Dose number 4 at 18 hours to 34. The time we want to calculate the level, the concentration, 18 to 34, the difference between them is 16 hours. Okay, so we just apply in the equation and then we get the results. How much will be the level? Okay, if no dose was missed, then you are not going to have this fraction in the equation. You're just calculating just a normal random level. So the concentration would be higher, but here you minus another fraction, so then you get a lower dose. Okay, you get a lower levels. You get lower levels. Okay, now let's move to calculation of drug levels after single and multiple intermittent infusions, and also let's see how to estimate the infusion rate and the dose given by intermittent intravenous infusion to achieve certain concentrations. This is what we used before, the same equation. If you remember, we used this equation before to calculate the drug concentration in plasma if steady state has not yet been achieved, and the condition, if you remember, for this equation, that the infusion must be going on, did not stop. The infusion is continuous up till this time, t. Okay? Because if infusion stopped before, then cannot be used. This equation cannot be used. Okay, so this is the equation for non-steady state if infusion is going on. So if infusion stopped, okay, once the infusion is stopped, so what is the time, what is the concentration at the time the infusion is stopped? Then instead of T, we use just T prime. T prime means the infusion time. So C stop, here the concentration of drug in plasma once the infusion stopped, same equation, but the time here is the time the infusion was stopped. We call it T prime. T prime is the infusion time. Okay? And we can use either this equation, having the infusion rate, this form, or we can replace infusion rate by the dose divided by infusion time. For example, if I give 100 milligram over 1 hour, then K naught equal to 100 milligram per hour. How about if I give over 2 hours, then K0 equal to 100 divided by 2, so the infusion rate is 50 milligram per hour. Okay, so the equation containing not the dose but containing the infusion rate. If you want to use it as it is, okay, if your infusion rate is 1 hour, if your infusion time is 1 hour, then put the dose as it is. It will represent K0. But if infusion time is different from 1 hour, maybe 0.5 hours, 2 hours, whatever, then you have to divide the dose by the infusion time in order to estimate the K0. Okay, so this is another form from the same equation. Then if we want to calculate the levels after this single infusion has stopped, then we have to multiply by the elimination fraction. This is the same equation of C2 equal to C1 times the elimination fraction. And this time is after infusion after the infusion was stopped. So this time is after the infusion was stopped. Let's practice so that we know how to use it. For example, here an antibiotic was infused with a 40 milligram over 2 hours. Assume K equal to 0.2 hour to the power minus 1 VD 10 liters. Calculate plasma drug concentration 2 hours after the start of the first infusion. Calculate the plasma drug concentration 5 hours after the infusion was started. So here we have to imagine what's going on. We mentioned that we started the infusion at time 0. The infusion is over 2 hours. So by 2 hours the infusion stopped, and then he wants us to calculate this level, C stop, since it is at the time the infusion was stopped, 2 hours after the start of the first infusion, and then calculate the plasma drug concentration 5 hours after the infusion was started. So if we calculate it from C stop, what's the time between them? From 2 to 5 is 3 hours. So first we calculate C stop using this equation, dose divided by T prime KVD multiplied by this fraction, and here T prime, this is the infusion time again. So 40 milligram divided by 2 times 0.2 times 10, okay, this is the K, this is the VD, and this is the infusion time, this is K. Substitute, you get 3.3 milligram per liter. What do you expect will happen to the concentration after stopping the infusion? We represented before the curve that we give infusion first time, so it will increase the level from 0. This is the concentration, this is time. So it will keep increasing the concentration. Okay, at 2 hours, we stop the infusion. Then the level is going to decrease based on elimination process, first order elimination, right? So it will be exponential decrease. So this is the C stop. And here we want to determine the concentration at 5 hours. So we determine it by the same equation. This Cp at 5 hours is the C stop multiplied by elimination fraction, but the time here is not 5 hours. The time here is the time between C stop and between the random level that we want to calculate. So it is 3 hours as we mentioned. So we multiply this level, 3.3, by the exponent of negative K times 3 hours. So the level obviously is decreasing. It will give 1.81 milligram per liter. At this time the concentration will be lower and will keep decreasing if no other dose will be given. So how about if multiple doses has been given? For the drug in example 7, 10 hours after completion of the first infusion, a second dose 40 milligram was infused again over 2 hours. Calculate the plasma drug concentration 5 hours after the second dose infusion was started. So let's imagine what's going on. The same in the previous example. We said infusion was given for 2 hours and then was stopped. The level, of course, will get decreasing after this. And then after we said 10 hours after completion of the first infusion. Completion means once we stop. Completion means once we stop. So 12 plus 10 is at 12 hours. 2 plus 10, 2 hours we stopped, and then 10 hours later means at 12 hours. Another infusion was given. Again, same thing for 2 hours. So by 14 hours, this is another C stop. Okay? So they want to calculate the plasma drug concentration 5 hours after the second dose infusion was started. So 5 hours from the start, not from the end of the second infusion. So second infusion started here. Add 5 hours to 12 will give you by 17 hours. I want to calculate the level. So how to calculate the level? You remember the superposition principle. We said the level at any point is the sum of the levels from all the doses. So how many doses was given here? 2 doses. So we need to calculate the concentration resulting from dose 1 or infusion 1, and we need to calculate the concentration both at this time point at 17 hours from the second infusion or infusion 2, and then we add them together. So Cp equal to Cp1 plus Cp2. The sum of concentrations resulting from both first and second doses or infusions. So how to calculate? Same thing, C stop times elimination fraction plus C stop times elimination fraction. So the first C-stop exactly will be the same C-stop because we are giving the same dose. Okay? We are not talking about together how much is C-stop. We're talking about everyone alone. How much will be the C-stop? We'll give the same value like what was calculated in the previous example. You apply the same equation like the previous example. C-stop equal to the dose divided by dose infusion time, KVD, times this fraction. Dose is the same. Two infusions, both infusions are the same dose, 40 milligram. Infusion time same, 2 hours, KVD same. Infusion time 2 hours same. So both of them will give the same result if given alone, independently. Okay? And then what will be different? The difference will be in the time since the infusion was stopped. In the time since the infusion was stopped. Okay, so since the infusion was stopped, infusion 1, then how many hours passed? From 2 to 17, we have 15 hours. But since the second infusion stopped, from 12 to 17, we have how many? We have only 5 hours. So in the first infusion, the ablation fraction time is 15 hours. Sorry, this one, the second infusion, since it was stopped, we say, so it's not from the start of the infusion. So since it was stopped from 14 up till 17 hours, this is 3 hours only, right? So here the time since C-stop is 15, here the time since C-stop is 3. So the result is the remaining concentration from infusion 1 will be 0.16. The remaining concentration from infusion 2 will be 1.8. So inside the body will be the total of both of them. So equal to 1.96 milligram per liter. So we're applying the superposition principle. Now we move to calculation of steady state drug levels after multiple intermittent infusions. So if the patient received multiple infusions, and you will study this in clinical pharmacokinetics later on, you will apply drugs, for example, like gentamicin or aminoglycosides in general, normally given by intermittent intravenous infusion. The dose is usually given by half to 1 hour infusion. So it's given as half-hour infusion or 1 hour infusion normally. And then you will practice there in clinical pharmacokinetics how to estimate the dose and infusion time that will be given and the tau to achieve certain levels. And if there is dosage regimen, you should be able to estimate or calculate the expected levels to be achieved by this dose. So what kind of equation we are going to use? This form, several forms we have. We can use this equation. This is the equation to calculate the main equation to calculate Cmax after multiple infusions once steady state has been achieved. And you cannot know, how can you know steady state achieved or no? Again, we can use the rule 5 half-lives. Okay, so you calculate 5 half-lives and you see by this dose that you want to calculate the level from it, was the steady state, did already 5 half-lives passed or no? If passed, then we are in steady state. If no, then we are not in steady state. So this is the main form. We can replace some forms. For example, you replace dose divided by T prime by K0. Okay? You can replace K times VD by clearance. So here you replace K times VD by clearance. And here you replace both dose divided by T prime by K0 and then KVD by clearance. So these equations are all the same. This one is same like this one, just different forms. We replace some values with equal values. Okay? So this one to calculate the Cmax at steady state. How about calculating Cmin? Cmin is calculated using the same first order elimination equation, C2 equal to C1 times elimination fraction. But be careful here to the time. In IV bolus administration, we just used tau in IV bolus. But here we must use tau minus T prime. Why? Okay, let's imagine the schedule. Time 0, you start the infusion. At T prime, you stop. The infusion, right? And then at tau, you start a second dose. Where is Cmax here? We drew the curve before, and we said the concentration will keep increasing till we stop the infusion. At T prime, we have Cmax. So Cmax now is not at time 0. Tmax is at T prime. Cmax is at T prime. And Cmin is here. So what is the time between Cmax and Cmin? It is equal to the dosage interval minus this fraction, this part, the T prime. So the time between Cmax and Cmin, time max to min equal to tau minus T prime. Okay? So here it is different from the equation used in IV bolus. Here the time between Cmax and Cmin is the tau minus T prime. Why? Because Cmax is not at time 0. Cmax here at the T prime time, the time we stop the infusion. Okay? If you rearrange this equation, same equation, this or this, then you can use it to calculate the volume of distribution. Rearrangement will give you this form. Okay? So let's practice. Here, example that you will have later in clinical pharmacokinetics again so many times. Gentamicin sulfate was given to an adult male patient by intermittent IV infusion. 1 hour IV infusions of 90 milligram of gentamicin was given. So here you should understand the meaning of these terms. If you say 1 hour infusion, then T prime equal to 1 hour. And then 90 milligram is the dose. IV infusion was given at 8-hour intervals, then means tau equal to 8 hours. Okay, gentamicin clearance is similar to creatinine clearance and was estimated as 7.2 liters per hour with an elimination half-life of 3 hours. Again, did not give the K directly. What is the plasma drug concentration after the first infusion? What is the steady state? Peak is max. Peak plasma drug concentration, Cmax, and the true, you can pronounce it true or trough plasma drug concentration, both are correct. So the trough plasma drug concentration equal to Cmin. They want you to calculate both. So here we will use non-steady state and steady state equation. But first we need to get the value of K. K equal to 0.693 divided by T half equal to 0.693 divided by 3 equal to 0.231. Drug concentration after first infusion, we use the non-steady state equation. C stop. Okay. They want the drug plasma concentration after the first IV infusion. They didn't give any time, means after the infusion finished. So means C stop. So equal to dose or K0 divided by KVD times this fraction. And we just replace, substitute the values. 90 divided by 1 hour, T prime. Clearance, we can use it instead of KV directly, 7.2. And then we get 2.58 milligram per liter. Okay, now we want to calculate Cmax or C stop at steady state and Cmin. Then we use the steady state equation and we use the form that is suitable for the data we have here. So we have dose every 1 hour, 90 milligram per hour infusion, so it's equal to K0. You can use directly this form, K0 divided by clearance that we have here in our equation. And we substitute the values, so 90 divided by 7.2, T prime is 1 hour, and tau is 8 hours. Tau is 8 hours, right? So we get, this is Cmax steady state, as we said at the end of infusion, so this is C stop steady state. How much the value? 3.06, which is larger than the C stop from the first dose. So this reflects what we mentioned about drug accumulation. If you give multiple doses, then drug keep increasing till reaching steady state. Okay, so calculate Cmin steady state. You just multiply Cmax by the elimination fraction using the time between Cmax and Cmin. And as we mentioned in IV infusion, the time between Cmax and Cmin is the difference between tau and T prime. It's the tau dosage interval minus the infusion time. So it is 8 minus 1 means there is 7 hours between them. Just multiply this level by the elimination fraction. Definitely you'll get a lower level, because this is an elimination phase, that the drug is being eliminated and the concentration will decrease, so giving 0.607. Okay, so now we want to think the opposite direction, that you have target concentrations and you want to achieve the dosage regimen. You want to calculate or estimate the dosage regimen to achieve these concentrations. So how you're going to calculate them? Number one, calculation of tau is using this equation, the same normal equation that we used in IV bolus, but the only difference would be this term. So we know that any time equal to ln C2 divided by C1 divided by K, isn't it? So if our time is the time between Cmax and Cmin, it should be equal to ln should be C1 divided by C2, okay? Cmax divided by Cmin divided by K. But the time between Cmax and Cmin equal to tau minus T prime, right? So you take T prime to the other side, then you get this equation. So tau equal to ln Cmax divided by Cmin divided by K plus T prime. So this is the equation for calculation of T prime in the infusion, intermittent intravenous infusion, short infusions. And how to calculate the infusion rate? The same previous equation for calculation of Cmax at steady state. We just transform, rearrange, so that we get K naught in the Y position that we want to calculate, K0. Okay, so previously it was Cmax equal to D divided by T prime times K times VD tau. So the same equation, you bring this one on the other side. Okay, so then it will be equal to Cmax multiplied by the denominator divided by the numerator. Okay, so you will get this form. Let's practice and see how to calculate. So the question will be like this form. They will give you target concentrations and pharmacokinetic parameters as well. Patient needs gentamicin, administered as 1 hour infusion, so you have already T prime in the problem, equal to 1 hour. Calculate the loading dose and dosage regimen to achieve a Cmax of 9 mg per liter and Cmin of 1 mg per liter. The new thing here is the loading dose. Okay, If we say that the target is 9 and 1, definitely we said before that we calculate the dose based on steady state concentrations. We consider them the target steady state concentrations and give you the pharmacokinetic parameters. So before talking about loading dose, just I jump to using the calculation of the dosage regimen. So dosage regimen, we calculate first tau equal to ln Cmax divided by Cmin at steady state divided by K plus infusion time. So equal to ln the target Cmax 9 divided by target Cmin 1 divided by K plus the T prime, the infusion time. So supposed to be 11.99 hours, so we just round to 12 hours. This is tau, and then we use this value in the equation for calculation of the dose, or K0. Here they are equal because infusion time is 1 hour. So the dose you calculate will be also infusion rate, but to continue only for 1 hour. Okay, so you just calculate Cmax, dose equal to Cmax times T prime KVD, this fraction containing the dosage interval, and this fraction divided by the fraction containing the infusion time. So just substitute the values. Cmax is 9, the target. 0.2 K, 14 is the volume distribution, 14 liters. VD is 14 liters. And then this is the tau value that we calculated previously in the previous step. And this is the infusion time that already given in the problem. So you get 126.4, you round to a convenient value, so we can suggest or recommend that the patient will receive 120 milligram gentamicin, 1 hour infusion every 12 hours. This is the dosage regimen. So now what about the loading dose? We mentioned before that with continuous dosing, the concentration will increase gradually till reaching steady state, and this time will take 5 half-lives at least, or you can say 7 half-lives ideally. Okay, so I don't want to wait till because this is infection, gentamicin given to treat infection. I want rapid effect, so I want to achieve effective concentrations immediately. So I give a loading dose that will achieve the target levels from the first dose. And then the function of the maintenance dose is to maintain the concentration. So in this case, first infusion, I need to give a larger dose. Decide you want to give as infusion or you give as IV bolus dose. So it depends on if it is specified in the problem, then we use the equation according to the dosing method. If not specified, just make it easy and follow the same dosing method. Okay. So assume that they ask you to calculate a loading dose as IV bolus. So IV bolus, CP node. Dose equal to CP node times volume of distribution. So you want to achieve 9 milligram immediately, you multiply by volume of distribution 14 liters, then you get the value of the loading dose given by IV bolus. But if you want to calculate the loading dose that to be delivered as infusion, then what you have to do is that use non-steady state equation for intravenous infusion. So this is 9 here will be our target C stop. So use the equation C stop equal to K node divided by KVD times this fraction that have the infusion time, and we just rearrange in order to calculate K0 instead of C stop. Calculate K0 instead of C stop. So this is the form of the equation after rearrangement. We just substitute. Our target C stop is 9. This is the K value, volume of distribution, they are constants, and the T prime. Okay, this is the K value. Then it turns up 139, so it's almost 140 milligram per hour. So the first infusion to be given is 140 milligram per hour. It will achieve a C stop or C max, but it is equal to the one that we need to achieve at steady state, that is 9 milligram per hour. By the end of this dosage interval, Cmin will be equal to Cmin steady state, which is expected to be 1. Okay? And then the next infusions that will be maintained will be according to the calculated one, 120 milligram. They will maintain the concentrations in the range between 9 and 1, Cmax, C stop or Cmax 9, and Cmin is 1 all the time, so they will maintain the steady state. Okay, so this is the way to calculate the dose and dosage interval for multiple IV infusions. We then go to the calculation for multiple oral doses, multiple dose regimen, oral administration. It will be almost the same concept. Can you see now the slides? Assumptions here. Okay, that the one compartment linear open model and first order absorption and elimination processes in order to use the following equations. So as we mentioned before, that the same graph will go with us all the time when we talk about multiple doses, that with multiple doses the concentration is continue to increase till reaching a steady state. With the increase in concentration, rate of elimination will increase. Once the rate of elimination equal to the rate of dosing, then concentrations will be stable in a fixed range. We don't have one concentration, we have a range of concentrations, Cmax and Cmin, but both of them will be stable. Cmax will be the same and Cmin after each dose, and Cmin will be the same at the end of each dosage interval. Okay, and then you have an equation to calculate the concentration after a number of doses before steady state has been achieved, such a bulky and complex equation, if you can see, and it depends on the number of doses. So the larger the doses you have, number of doses, the larger will be the concentration. Okay, but this equation has two forms actually. Either, if you see here, we have both. We have now an oral absorption, an oral administration. The equation contains absorption rate constant and contains elimination rate constant, right? So look at the location. Here, this form, K minus Ka. In this form, Ka minus K. Subsequently, if you reverse the arrangement here also will be reversed. So here Ka first, but here Kt first. Okay? So we have two forms. You can use any of them, either, doesn't matter. The calculation is just direct, same like the previous slides when we talk about multiple IV infusions or IV bolus, the same thing. You want to calculate certain levels after number of doses. So first you based on T-half, you verify whether steady state has been achieved or no. If steady state has been achieved, then you can use the steady state equation. If not achieved, you have to use non-steady state equation. And again, the same concept. Steady state equation can be used only at steady state, but non-steady state equation can be used all the time. Whether steady state achieved or not achieved, it will give you a correct results. Okay? So here the problem is patient is started on a drug at an oral dose of 100 milligram every 6 hours. Assume a one compartment linear model. So here the dose is 100 milligram. Dosage interval is, the tau is 6 hours, and you have the value of bioavailability. Now we have to use F in case of oral absorption. 0.51 means 51%. Ka 1.48, T half is 4, Vd is 48.3. So again, you can calculate the time to achieve steady state. 5 T half equal to, T half is not available, 4 hours. So 5 times 4 equal to 20 hours. Okay, they want drug concentration 3 hours after the first dose. So first dose is at time 0, 3 hours after this 3 hour only. So non-steady state. 2 hours after the second dose. Second dose is after one dosage interval. So at time 0 again, remember this one dose, second dose at 6 hours, 1 tau. So they want 2 hours after second dose means after 8 hours, still no steady state. 1 hour after the third dose. Dose 3 is 2 intervals, 12 hours. 12 plus 1, 2 hours after this dose means at 13 hours. So still steady state has not been achieved. So now you have to use non-steady state equation. You cannot use steady state equation. So just substitute. This one Ka, this one absorption rate constant. K is not given, so we calculate K from the T half. K equal to 0.693 divided by T half equal to 0.17325. The rest will be just a substitution. The most important is to know how to substitute. Here we say after the first dose means N equal to 1. If N is equal to 1, you can just use the original equation that we used in the first lecture when we discussed about oral absorption. That this simple equation that doesn't contain the term N doses, since we are talking about one dose. If you apply in this equation, still this equal, doesn't matter, it will give you correct value, but it is bulky equation, so no need to use. But if we have more than one dose, then we have to start to use the big equation that contains the number of doses. So just to substitute the values: bioavailability value, dose, absorption rate constant, volume of distribution, elimination rate constant, absorption rate constant, and so on. Number of doses here is 2 doses. 2 hours later, this is the 2 hours. This is the time small. T small is the time after the dose. You substitute it here. Here you substitute tau. Tau is 6 hours. Okay? So you get a result that is 1.082. Okay, same equation if you want to calculate 1 hour after 3 doses, then N equal to 3. And T small equal to 1. The rest of the equation is same like the previous one because we are talking about the same dose and same dosage interval. The level is 1.215. So just a substitution. Okay. How about if there are non-uniform multiple doses? So again, you will use the superposition principle. Okay, and will not stop by it too much. But if you have non-uniform multiple doses, means, for example, first time the patient first dose was 100 milligram, and after 8 hours maybe he took 200 milligrams. After not 8 hours again, maybe after 5 hours again or 10 hours again, different value, then the patient received probably 150 milligrams. So how to calculate this one? Superposition principle. We draw the same line. We draw the same timeline. And then, okay, time 0. Dose 1 equal to how much was given. And then at what time the second dose was given. At what time the third dose was given. What time we want to determine the concentration. So the concentration here will be equal to sum of concentration from first dose and concentration from second dose, C2, and concentration from third dose, C3. Which equation to use? Non-steady state equation. For all of them, the same thing. Okay? And for each of them, we use the dose that was received that will result in this concentration and the time since this dose. Okay? K and Ka will be the same because they are for the same drug. Volume distribution will be the same in all the equations because for the same drug. Bioavailability will be the same because same drug. Okay? This is how to estimate. Example here, a patient is started on a drug at an oral dose 30 milligram at time 0, 125 milligram at 12 hours, and 150 milligram at 24 hours. And giving you the pharmacokinetic parameters, F equal to how much, Ka equal to how much, K equal to how much, Vd equal to how much. Vd here, notice that it is liter per kg, so I have to multiply it by the body weight. Okay, calculate the drug concentration 2 hours after second dose, 1 hour after the third dose. So you have to draw the line. So here we are mentioning about at time 0, the patient took 30 milligram. And after 12 hours, the patient took 125 milligram. And at 24 hours, the patient took 150 milligram. Calculate the concentration 2 hours after second dose. 2 hours after second dose means here, 14 hours. They want the concentration. It will be equal to concentration from 14 hours after first dose plus concentration 2 hours after the second dose. So we use this equation, the same, and then we replace the same values for F, Vd, K, and Ka. The difference will be in the time and in the dose. The dose, first dose, is 30 milligram, but second dose is 125. The time from first dose is 14 hours as we calculated in the shape. The time from the second dose is 2 hours. So we add the two concentrations together and then we get the result. Calculate the level 1 hour after the third dose. 1 hour after the third dose, then we have 3 levels. This is at 25. So concentration 25 hours from first dose. And 25 to 12 is 13 hours from the second dose. And 1 hour from the third dose. So again, the same equation 3 times, you add them together. The difference will be in the dose, 30. The second equation, the dose 125. The third dose is 150. And the other difference in the time, so the first one is 25 hours, the time of between concentration and the dose. And then the second concentration resulting from the second dose, we have 13 hours between the level and the second dose, and we have 1 hour between the level from the third dose and the third dose. We calculate the result of each equation and then we add them together. The value should be this amount. The easier one or smaller is the steady state plasma drug concentration. We can calculate at steady state either average steady state concentration or we can calculate the Cmax and Cmin. If you want more, once you go clinical pharmacokinetics, then more oftenly you will use the average steady state drug concentration in calculation, and the equation is very simple. As I told you, the original equation is AUC divided by tau, and AUC is replaced by F dose divided by KVD. Okay, so this is very simple equation. Tmax is calculated with some, if you want to estimate Tmax, this is the equation for at steady state. If you want to, it's more complicated than before steady state that we used in the previous lecture for single dose oral administration. And Cmax can be used using this equation. Cmax at steady state can be used using this equation, can be calculated using this equation. And the time here is Tmax definitely. So we need to calculate Tmax first. If we calculate Cmax, then we can calculate Cmin from it. And Cmin cannot be, you cannot say Cmin equal to Cmax times elimination fraction. This is wrong. Why wrong? Because if you remember, Cmax in the dosage in the plasma versus time concentration, After Cmax, there are two processes still going on. Still there is absorption plus elimination, and then will be elimination only, right? So there is not only elimination. If there is only elimination, that will decrease the level from Cmax to Cmin, like in case of IV, then I will just use this simple equation, this one. But no, between Cmax and Cmin, there are two processes, absorption and elimination. So the equation must contain both, contains term for absorption and contains a term for elimination. So this is the equation that can be used for calculation of Cmin, this or this. Okay, let's practice an example. Drug was given by multiple oral doses of 125 milligram every 8 hours. Assume one compartment linear model applies to this drug. Bioavailability is 0.57, absorption rate constant 2.63, half-life and VD 3.1 hour and 0.66 liter per kg. Calculate steady state average drug concentration, CP, average, SS. So use the equation that contain K and VD or clearance, whatever the data is available for you easily. So we don't have clearance, we don't have K, we calculate K first. Volume distribution is not also available directly. You have to multiply by body weight. So first you have to calculate K from the T-half, 0.693 divided by T-half, equal to 0.2235. You calculate volume distribution, multiply the body weight by the volume distribution per kg. Okay, body weight times volume distribution liter per kg. So the total volume distribution is 31.944. Then simply you apply in this equation. CV average steady state concentration is equal to F times dose divided by KVD tau. And all the data now available. F is 0.57 from the problem. Dose is given already in the problem, 125 milligram. K, volume distribution, and tau. Tau is given as, we said, every 8 hours. When we say the drug is taken every 8 hours, then the dosage interval is 8 hours, which is tau. So the average steady state concentration is about 1.247 milligram per liter. Now we take it, we reverse it the other direction. Antibiotic is available as tablets, as decided to be given in 500 milligram doses. So they give you the dose, but then, and they give you the target concentration to be achieved, average steady state concentration, 15 milligram per liter. And they want you to calculate the dosage interval, tau. So you use the same form, which is, the form was C average steady state equal to F dose divided by K VD tau. So you want to calculate tau, then tau will be equal to C average steady state. You take tau to the other side and you take this C average down there, so it will be equal to F dose divided by KVD C average. That is just the rearrangement for the same equation. So you just substitute. F is 0.9 as in the problem, 500 milligram doses. This is the value of K given, the value of volume distribution given, and the target average steady state concentration. Then tau is 8.65 hours. So you can recommend this, or you just round to 9, but rounding to 9 hours means make it longer. Then you will achieve slightly little than 15, probably 14 or 13 something. Okay. Another example that we have target average concentration and tau, but we need to calculate the dose to achieve these levels. So here a drug given by multiple oral doses every 6 hours. After consideration of the patient's clinical condition, we want the average steady state concentration to be 15 milligram per liter. Assume one compartment linear open model for this dosage. The bioavailability is 0.82, Ka is given, patient weight is 92.1, T half is 3 hour, Vd is whatever. Calculate the dose that will achieve this one. So same equation, just rearrangement. So the rearrangement will give you that dose equal to average steady state times kVd tau divided by F. This equation very commonly will be used during the clinical pharmacokinetics course when you calculate the dose of oral dosage forms or the drugs taken by oral route. Most probably you will use the average steady state concentration, and here to calculate the dose just substitute. The target concentration is 15 milligram per liter, value of K, value of volume distribution, the tau given in the problem also every 6 hours, right? Every 6 hours. So tau is 6 hours, and then divide by bioavailability 0.82. You get the dose, suppose dose 770. You can also do rounding when you practice in the hospital. Depends on the dosage form available. You have, for example, 200, how much here we say? It's not given here the available strength, but if I told you, for example, it is available as 250 milligram tablet, you can round to multiples of 250, right? So you can suggest 750, so the patient will take 3 tablets every 6 hours, and so on. Say, for example, 500 milligram tablets. Then you can suggest 1.5 tablet. If I told you available as 400 milligram tablet, then you better round to 800, so the patient will take 2 tablets every 6 hours, and so on. Now, if I want to calculate the Cmax, I should use the equation for Cmax. So another example, here, give you the dosage interval every 24 hours, and then pharmacokinetic parameters, including bioavailability also, and Ka. They want you to calculate average, min, and max at steady state. So use steady state equations. C average, you just use the same formula, substitute the values, you have tau 24 hours, volume distribution, K, bioavailability, and the dose. So C average is 0.772. Okay? Then to calculate Cmax, you need first to know the Tmax, because in the equation you have Tmax. The equation for Cmax, you calculate the time at the concentration at Tmax. The time is Tmax. So first you need to estimate Tmax, so use its equation. Don't worry, will be provided to you. So equal to 1 divided by Ka minus K ln Ka times this fraction, divided by K times this fraction. You just substitute the values for Ka, K, Ka, K, tau, K and Ka, and then you calculate, you get the result 1.19 hours. Then you use this value in the equation for Cmax. Substitute again the values, the dose 250 milligram, tau 24 hours, Tmax 1.19, the values of K, that is 0.229, then done. Cmax is 3.25. Cmin, as we said here, you cannot calculate simply by multiplying by elimination fraction. It has its own equation because there is absorption in a process going on between Cmax and Cmin. So you have an equation containing both Ka and K. Just substitute again the values equal to Ka, which is 2.09, divided by times bioavailability, which is 0.76, times dose, which is 250 milligram, times e to the power negative k, 0.229, times tau, 24 hours, divided by Vd, 44.8 times 2.89 Ka minus 0.229 the K times 1 negative K times tau 24. Then the result is equal to 0.02 milligram per liter. Okay. Now we need to calculate a loading dose that will achieve a higher concentration. Loading dose is the one that will immediately achieve the target average concentration. So we just divide by volume of distribution. Simply the equation is, because loading dose also will be given by oral route. So actually we are calculating like, we are using a form like, simple like this, dose equal to concentration, the target concentration, times Vd. However, this dose will not reach 100% to the circulation, so we have to divide by F. And depends, if you are giving the parent drug, then nothing else in the equation, but if you are giving salt, then you have to divide by salt fraction also. Okay, so for example, you want the concentration is always measured in the parent molecule. For example, you are giving phenytoin sodium. Concentration is measured as only phenytoin, not as phenytoin sodium. Okay, so you have to give more in order to of phenytoin sodium to give the necessary amount of phenytoin that you need. So for example, 0.8 of phenytoin sodium is phenytoin. Then the amount of phenytoin you need to deliver to achieve this one is calculated like this. This dose actually will be, if you didn't use the S, will be the dose of phenytoin. But once you divide by S, it will give you phenytoin sodium dose to be given to the patient. Okay, so here in this example, C average is approximately, it's given you the okay, so as we discussed here, as I explained, we give loading dose so that we achieve immediately the average steady state. We don't wait after the first dose, and we don't wait to have what? We don't wait for about 5 to 7 half-lives to achieve the steady state concentrations. The same concept we explained before. Loading dose actually can be given oral, can be given IV infusion, can be given by short infusion or by IV bolus or orally. If it is orally given, then you have to use this equation. If still also given by IV, probably also use this equation and so on. Okay, let's practice. Calculate the phenytoin sodium dose to achieve target average steady state phenytoin concentration 15 milligram per liter, and F equal to 0.9, S is 0.8, Vd is 20 liter. So the loading dose will be equal to the target steady state concentration times volume distribution divided by F and S. So the target concentration, as in the problem here, is 15. We want to achieve volume distribution 20 liters. Bioavailability is 0.9 and salt fraction is 0.8. 0.8 here means that 80% of phenytoin sodium is phenytoin. Okay, so how much phenytoin sodium? This dose, you calculated how many milligram. This dose will be phenytoin sodium dose, not phenytoin. But this concentration is phenytoin concentration. Once we measure the free drug, not the salt. Okay, so when we say that the level is 15 milligram, it is phenytoin level. You can see here, we didn't say phenytoin sodium, phenytoin concentration, not finite sodium concentration. Here, calculate the digoxin loading dose to achieve target steady state concentration of digoxin, 1 microgram per liter, knowing that F equal to VD equal to. So the loading dose will be same unit, don't forget. Here milligram per liter, the dose milligram. Here dose should be microgram. So average steady state concentration 1 times VD 20 divided by bioavailability. Why we didn't use S value? Because the level is digoxin, the dose is digoxin dose. Okay? So the dose is also digoxin. We didn't use any salt. So the value is equal to 1. Because 100% of digoxin is digoxin, right? And then you can calculate how much should be the loading dose. Now we finished the multiple dosing, and we can have like 5 minutes break, and then we need to continue with another topic. We'll just teach part of it, and then next after Eid, inshallah, we continue the remaining part. Okay, let's have a 5 or 7 minutes break.